Hey, welcome to day 3 of the flipped class experiment. Trying to get my voice to be at a good volume so that you can hear me without any major concerns. So, if I sound like I'm yelling, it's because I probably am talking a little louder than I might normally, sitting in a room by myself. So, the topic is today is volumes of solids of revolution, and the particular portion that we're talking about is what's called the disk method. And the reason it's called the disk method will become clear fairly soon. So, what we're talking about is basically taking some sort of a plane shape, perhaps something like that, and spinning it about one of our axes. So perhaps about the x-axis in this case. So we're going to take this plane shape, spin it out of the screen, back into the screen, and we're going to get a three-dimensional object. What three-dimensional object, you might ask? Well, this particular one here, I could actually click on it. There it is. Okay, might be cucumber. Okay, picture the cucumber. Another one that I might do is maybe I would take a shape that's sort of like that one, maybe a little smaller, a little taller, and again, spin this about that particular axis. And what I would get in that case might be something that's more like a kiwi. Okay, maybe it's should be a little longer, but the general idea that some sort of a solid that we're working through there. The last sort of example that I'll show you would be, and this is going to be a little more difficult for me to draw, so I'll just take my time. A shape, perhaps, like that. Okay, if I take that shape, and it would be a composite of a bunch of curves, and I were to spin it about the x-axis again, I would get some sort of three-dimensional object. Okay, not a cucumber, not a kiwi, but something that you've probably seen before if you've been paying any kind of attention in your world. Okay, so what shape? I'll give you the actual real-life version of it. It's a little different than the drawing I gave because I tried to draw something that looked like a function. This one isn't really a function, but it does have a function. Okay, as I take this object and I rotate it about an axis, I begin to get this shape right here. You might recognize a little fancy three-dimensional bell, or you probably had them with at your birthday parties and things like that in different shapes, but it starts as flat and you rotate it around and you get a three-dimensional object. Okay, here's the three-dimensional object again. It's the wedding bell. These are actually from my wedding. I got married. Don't ask. As it turns out, you can see on this particular version, there's some rings that you'll be able to see, and you'll be able to see a little better in this next picture of the same object where the bell shape appears, if I stop in the right place, to be floating. So these rings that I've drawn around here are going to become important as we try to figure out how to figure out the volume of shapes like that that are formed by rotating a plane shape around an axis. Okay, let's go back to the cucumber so that we can sort of make sense between how we might get from a plane shape to a volume. Okay, so there's a cucumber. This is the one that we got by just rotating that shape around an axis. We get the cucumber shape. These little things are slices. If I take all these slices and put them back together without eating any of them, I would get the cucumber back. You know, if I just slice this cucumber randomly in a bunch of places, and I get this sort of disc shape. Ooh, the disc method. So I could calculate the area of this cucumbery face right up here. I could multiply by the thickness of my cucumbery face, and if I added up all these cucumber slices, I'd get the volume of the entire cucumber. And that's this general thing that we're doing here. Obviously, we want our cucumber slices to be as thin as possible to, take into account or eliminate the effect of the curve, the fact that it's not a nice, perfectly smooth thing. If we slice it too thin, then we'll get like some error there. So that's what we're after, is we're trying to figure out how to find the area of these discs. And then we'll multiply by the thickness, and then we'll add them all up, which is essentially what we did yesterday with the squares and triangles, but today they're circles, so that's a little easier for us to deal with. Okay? So let's forget about fruits and vegetables and other things and just get into some mathy versions of things. Okay? So the first thing we're going to do is going to take the square root of the sine of x, and we're going to rotate it about the x-axis. And we're just looking at this little portion of it that's right here in this first section, and this is actually from 0 to, where is it from? 0 to 2, 0 to pi, I guess it is, from 0 to pi. So we'll look at this particular piece here. When we rotate this shape about the x-axis, we're going to get some sort of a three-dimensional object. Three-dimensional object might, this may be a bit of a stretch, look sort of like one of these little vitamin capsules or something like that. Okay, if you make it a little longer, but the basic idea is we're going to get some sort of three-dimensional cylindrically shaped thing. So, like we did yesterday, first thing we need to do is we need to figure out what the area is. Go back to a different color pen. So, the area of a circle, because what we're going to do is we're just going to take a slice right here. Okay? And this slice is the thing that gets rotated. When we rotate that slice, we get a circle. Okay? The circle has a radius. The radius is the function. So the area of a circle we know to be pi r squared. Pi, my radius, is just the function itself, the square root of the sine of x squared. So that's how we get the area of one slice. To turn that into a volume of a slice, we're just going to multiply the area by the thickness, just like we did yesterday. Okay, in this case, my area is pi square root of the sine of x squared. Thickness we're going to call delta x. That gets me one slice. We want all the slices. Going back to the cucumber analogy, we want to add up all the little slices of whatever this shape is. And the way we do that is with calculus. We integrate. We integrate pi times the square root of the sine of x squared dx. The delta x becomes dx because our slices get infinitely thin. We're going to do a definite integral. We're going to integrate, in this case, from 0 to pi. And we should end up with a nice little volume force. It's a relatively easy one to deal with. The pi usually we put out in front of the integration sign, 0 to pi. Hopefully it's been bugging you that I've been doing the square root of sine and the squared part, knowing that those just take care of each other. So we end up with the integral of the sine of x dx, which we all can do, so I'm not going to go further with that. We know the antiderivative of sine, and then we can evaluate it at pi and at 0 and come up with an answer. So if you wanted to finish out the problem and get an actual volume, that would be great. That would tell us the volume when we rotate this thing about the axis. Okay? Just want to check my time. Hang on for a second. Doing great. 8 minutes. So next one. Find the volume of the solid when the region defined by, in this case, 2 minus x squared, which is this, and x equals or y equals 1. Okay, this whole region right in through here, all of this stuff. Well, let me get the highlighter out. This region is what we're rotating, and we're rotating it about that line. Okay? So just again for the visual, what's that look like? Maybe it looks like an M&M. I don't know. It looks like a peanut M&M if we take this. I did it in yellow, so that would be the peanut guy. But again, what we need to do, figure out what's a slice. That's the thing that we're rotating about this line. So we need to figure out its radius, figure out the area, and so forth. So the area we know to be pi times the radius squared. What's the radius? Going back from that area between planes piece, the area is going to, or the radius, sorry, is going to be the difference between these two slices. So my radius is going to be 2 minus x squared minus 1, which turns out to be 1 minus x squared. Okay, so my area is going to be pi times 1 minus x squared squared. Volume, pi times 1 minus x squared squared times delta x, the thickness of a slice. Okay, that gets me one slice. I want all the slices in this case, right? So I'm going to integrate pi, and let's put the pi right out in front right away, 1 minus x squared squared, and delta x becomes dx because we're getting really thin. Only thing we don't know is from where to where are we integrating, okay? We could look and say, oh gosh, it looks like it's about 1. Maybe it is, maybe it isn't, but let's not guess. Let's find out where they actually intersect. So let's just say when is 2 minus x squared equal to 1? I think that would be when x squared minus 1 is equal to 0, which turns out to factor as x plus 1, x minus 1. So my lower limit is going to be negative 1. My upper limit is going to be positive 1. And again, get your calculator. You can do this work. This is not really the point. The calculator to do the work. You could do this work. Remember, if we did this by ourselves, we'd need to expand this piece out. Okay? One last example, slightly different, but same concept. Okay? In this case, this time we're going to rotate. We've got the same information. We've got some sort of a solid. Okay? And we're going to find the volume when the region is defined by x to the 2/3, which is this thing here, and y equals 1 is rotated about the y-axis. Okay, so the region we're talking about is this little zone in there, and the rotation this time is about the y-axis. Okay, so when we're doing the disk method, we always want our slices to be perpendicular to the axis of rotation. So our slice is perpendicular and you might have heard me hesitate for a bit when I said perpendicular, because usually what I'll say in this case is we want it to be let me finish my thought. Sorry. Okay, usually what I'll say is for the disk method, we want our slice to be perpendicular to the axis of rotation. If you were here, you'd be laughing. Okay, so slice is going to be perpendicular to the axis of rotation. So that means that we're not looking at y equals x to the 2/3. We're looking for x as some function of y. No big deal. We can easily make this x as a function of y. So if y is equal to x to the 2/3, what I can do is I can multiply or raise this side to the 3/2. If I do that to that side, I've got to do that to this side. 2/3 times 3/2 gives me 1. So I get x equals y to the 3/2. That's this function right here. Okay, that's this right here. That's my radius. Okay? But the story remains the same. We still have got to find the area. The area still is pi times my radius, y to the 3/2 squared. Okay? My volume of a slice is still going to be the same thing. Pi times y to the 3/2 squared times delta x. My overall volume is still going to be an integral. It's going to be the integral, in this case, from 0 to 1, because we're moving our slices up the y-axis from 0 to 1. And so it's going to turn out, going to get the pi out of the way in the front. Y to the 3/2 squared just becomes y cubed dy. Okay, let's see, do we have time to actually do this one out? Well, probably, maybe, but I think you can as well. You can do this one by hand. If you do it on the calculator, you can still plug in the x value and you'll get an answer. Okay, so the thing I'm going to say over and over and over again as we go through these, figure out what the area looks like, the area of one slice, figure out how to turn that area into a volume just by multiplying by thickness. To get them all, we integrate. Okay, and the integration part turns out to be the easy part at this stage of the game. Okay, and for the disk method, we want our slices to be perpendicular. Okie dokie. Got questions? Bring them in. Hopefully this was a little louder, clearer. We'll see you tomorrow. Thanks for watching.